Anthony Short, our next speaker, will be talking about the I/O services provided by OS2 for applications with simple character-based user interfaces, applications that don't do any character I/O at all, and family API applications. Anthony has been working with Gordon Letwin for the last 2.5 years as one of the original members of the OS2 design team. In that time, he's concentrated his efforts on the I/O design issues of OS2.
My talk is going to cover two main areas of OS2. First, I'll be covering character applications. These are a class of applications that are written to not use any of the presentation manager services. We'll see that the main area of difference between a character application and a presentation manager application is in the area of I/O, particularly the keyboard, the screen, and the mouse. The second part of my talk will cover what we call family applications. These are character applications written to a subset of the character application interfaces and are able to run under OS2 and under MS-DOS. Most of what I'm covering today will be relevant to those of you writing applications and experimenting with the first software development kits from Microsoft. It'll also be very interesting to those of you migrating applications from the MS-DOS 3.0 environment. Finally, towards the end of my talk, I'll be covering the debugging tools available for your applications under OS2. Let's first take a look at the types of applications that are suitable for being built as character applications. There's three real categories that we've identified. The first are applications with very simple character-based user interfaces, something like an assembler or a linker, where you have a command line with some arguments and maybe a few error messages when the program terminates. If you look at the software development kit from Microsoft, you'll see that the language tools we provide are built with this type of interface. The second category of character applications are those with no user interface. For example, a sort package which is designed to be executed by another application rather than to interface directly with the user. Or maybe a time-critical application which is interacting with a device driver rather than with the user. And then the third category is what we call daemon or background processes, something like a print spooler or a network server. These processes typically are continuously running, sitting in the background, and generally the user is not aware of their existence. If these programs need to interact with the user, they usually do so through a separate user interface program. Overall, I would say that character applications will not be the majority case of OS2 applications, but initially many people will write character applications as they're migrating things from DOS 3 environment. Let's take a little look at the difference between the MS-DOS environment and OS2. Under MS-DOS, Microsoft Windows is an optional part of the system, and many applications today are written to not use Microsoft Windows. Under OS2, every system will have the graphical presentation manager present, and therefore we expect that most applications will be written to use it. However, it will still always be possible to write character applications. I'd like to take a look at the various ways from a user perspective that character applications can be started. There's the straightforward command line interface using the command interpreter, where you type the name of the command at the prompt. This is very similar to the DOS 3 environment today. Then we have a new way of starting applications from the command line using the start command. From the application's viewpoint, this is the same as the normal command line interface. From the user's perspective, the difference is the application is started in a new screen group rather than in the current screen group. So the user will then have to switch to that new screen group in order to interact with the application. Then we have the detach and run commands. I'll be discussing these in more detail in a minute. These are a method of putting applications into the background. Then also character applications can be started from the Windows Presentation Manager. And there are two types of character applications. One sort can coexist on the Windows Presentation Manager desktop, and I'll be discussing later the restrictions and caveats that you need to follow to ensure your application can do this. And then If your application does not follow these rules, we have the second category where Windows will start your application in a new screen group in full screen mode rather than in a window on the desktop. All of these methods of starting applications all use internally the DOS exec program system call, which has parameters to indicate whether the child process should execute synchronously or asynchronously with the parent. Now, to take a more detailed look at detach and run, detach is a user command which is used to start a background process. If you've used Unix or Xenix, you'll see this is very similar to putting ampersand at the end of the command line. The run command, from the application standpoint, is identical to detach. The only difference is that run is a config.sys statement that the user puts in his configuration file and is executed at boot up time, whereas detach is a user command that can be typed at the keyboard at any time while the system is running. I think run will be rarely used. It's mainly designed for those few cases where you need to start a background process very early on in the life of the system, before the user shell is started. And as I said before, the DOS exec program is a system call, is a applications interface for you to start other applications from within your application, either synchronously or asynchronously. Now, if you start a detached process, there's a few restrictions from the user standpoint and a few restrictions from the program standpoint that you need to be aware of. First two bullets on the slide show the user's perspective. These applications are fully detached from any user interface. They do not appear on the application selector list. You cannot switch to a screen group containing these applications. And as far as the user is concerned, these apps do not exist. They're designed for background service type functions that the user doesn't need to interact with. From the application standpoint, a detached process can't do mouse or keyboard input via any normal means. I'll be discussing later something called device monitors, which is a specialized mechanism for getting character input. Likewise, background applications cannot do screen output via normal means. We have a mechanism called pop-up screens for emergency messages. I'll be discussing that later too. Since these applications have no keyboard input, they have to provide some dedicated means for termination, if indeed they need to terminate. You can't type Control-C or quit or exit. And finally, since these applications are essentially unknown to the user, they generally have to expect to handle a wider range of errors. It wouldn't be satisfactory to have a background application causing hard errors on the floppy drive because the drive door is open. If the user doesn't know about this process, he's going to find it very difficult to recover from any errors that it causes. Now I'd like to move on to look at some of the programming aspects of a character application. Here we see the simplest possible character application written in C that prints hello on the screen. And as you see, it's very familiar to those of you who have used Microsoft C 4.0 in the DOS 3 environment or programmed in C in a Unix or Xenix environment. There's a function main which is called on startup. This example also shows how you can call the OS2 operating system directly from a high-level language. The VIO write TTY function is a OS2 applications interface. There's no C runtime involved in processing this call. As I said earlier, the three main areas of difference between character applications and those written to the presentation manager are the keyboard, the screen, and the mouse, since these are the three devices that are managed by the presentation manager. If you write a character application, all of the other OS2 interfaces such as multitasking services, memory management, inter-process communication, dynamic linking, all of those are exactly the same whether you're using the presentation manager or not. First, I'd like to take a look at keyboard input. When you look at the software development kit, you'll see there's a large set of function calls beginning KBD. These provide a set of services that are roughly analogous to the interrupt 16 run BIOS calls that are available in real mode. It's important to note that these functions are provided by the operating system, not by run BIOS in the machine. This ensures a greater hardware independence and a greater portability between different machines and different implementations of OS2. Now I want to take a look at some special keyboard services that will not be used by normal applications for input. The first area I want to cover is what we call device monitors. I'll be discussing this in the context of the keyboard device, since that's the common case, but in fact it applies to other devices as well. The device monitor concept provides a standard method for intercepting the data stream of a character device. This can be used to implement a keyboard macro package, or to implement a pop-up package that comes alive when a certain hotkey is pressed, or to implement spooling if you wish to intercept all character output to a certain device and spool it to a file. Those of you who are familiar with the DOS3 environment will see that this is very similar to the type of thing people do with terminate and stay resident programs in that environment. Now, device monitors can be applied to any character device under OS2. However, it requires device driver support, so not all character devices will necessarily support monitors. Under the standard product on the PCAT, we support monitoring of the keyboard, the mouse, and the printer. And as I said before, from an application standpoint, the keyboard is probably the most useful of these three. Now this diagram shows how character device monitors work. At the bottom of the screen, you see a device driver. This is a character device driver, such as the keyboard driver. Then in the middle we have the operating system, which processes application I/O requests. Over on the right-hand side, there's an OS2 application that is called DOS read to request some data from the character device. The DOS read request goes to the operating system file system component, which routes the request down to the device driver. Now on the top of the screen on the left and in the center, we have two monitor applications which are filtering the data stream from this character device. When a character arrives, say the user presses a key, the device driver first sends the data to the first monitor application in the chain. Each monitor application has two buffers which it provides. The operating system places data in the first buffer for the application to process, and then the second buffer is used to put data in for the operating system to take back. So the data essentially flows into one buffer, the application processes it, puts it in the second buffer, the operating system takes it back. And there can be any reasonable small number of monitor applications on the chain. When the last application in the chain has finished processing the data, it goes back to the device driver, and from there back to the OS2 application. Important to note that the device driver has control at both ends of the chain. Now let's look at the application interfaces for using device monitors. We have the open and close calls, which are very similar to normal file open and close calls. They establish a connection to the device and return a handle. And then there's the register call, which is used to tell the operating system where your two buffers are in your application for attaching to the chain. Then we have the DOSMon read and DOSMon write calls, which are used to read and write data to the character device stream. Now, there's a number of special characteristics of device monitors which require some care when you're writing monitor applications. First thing to note is that the format of the data which passes down the chain is specific to the device driver you're working with. There is no standard device driver format that applies to all devices. As an example, the keyboard driver will timestamp all the packets that come down the chain, whereas on a printer that really isn't necessary, so we don't have a timestamp field. Some devices may be able to put several characters in one packet. The printer, for instance, does this. The keyboard driver, however, has to put one character in each packet, since the user expects keystrokes to be processed when he types them rather than buffered up. Now, the monitor application must be very careful not to delay the passage of data down the chain. We recommend that you provide a dedicated thread in your application that will read data, process it quickly, and pass it on to the next buffer. If you stop to do slow disk I/O or wait on semaphores or do other slow operations, the user could potentially see a very long delay in his keystrokes being recognized. Obviously, each monitor application on the chain adds some overhead in passing data through the chain. There's a task switch involved to go from one monitor application to the next. So device monitors are most appropriate for relatively slow speed devices. The keyboard is the most suitable. Printer and mouse, we also provide device monitors. We chose not to provide monitors for the async driver because for performance reasons it would be very difficult to support the high speeds. Another restriction worth noting is you cannot intercept the system hotkeys with device monitors. And another aspect of device monitors is that individual devices can decide how many chains they will support. The devices that are virtualized on a per screen group basis, such as the keyboard and the mouse, they provide one monitor chain per screen group. So your monitor application can choose to monitor all of the keystrokes in the system or just those in one screen group. The devices such as the printer, which aren't virtualized per screen group, tend to provide one monitor chain per logical device. In the case of the printers on the PC, you get LPT 1, 2, and 3. Now we move on to look at screen output. Just as in the case of the keyboard, we have a set of function calls that correspond to the interrupt 10 BIOS functions that you may be used to in real mode. You will see these all begin VIO for video input output. These are, just like the keyboard functions, implemented in OS2 rather than in the ROM BIOS. The VIO functions generally are a superset of int10. Performance is better, and some of the functions such as 43 line mode on the EEGA are supported. And also VIO character output generally continues to run when your application is in a background screen group. Here we see some examples of common character output functions for the screen. There's TTY mode output. There are a full set of cursor positioning functions. There's full set of scroll functions which will scroll any rectangle on the screen up, down, left or right. And then there's an optional ANSI emulation package built in. This can be enabled or disabled on a per screen group basis. These are the type of functions that your character application will use to do normal screen output. Now I want to take a look at a couple of the functions I mentioned earlier, which are what we call special screen functions. First is pop-up screens. There's a system called VIO pop-up, which will allow you to output to the screen on top of the currently running application. This is very useful if you have a background process such as a print spooler, which suddenly needs to notify the operator that the printer is out of paper, for example. The pop-up routine allows you to put up a message on the screen and then receive some keyboard input from the user, regardless of what application is currently running on the screen. And then when you take down the pop-up, the screen will be restored to what it was before. Whether or not the screen is restored by the operating system depends on the type of application that's running in the foreground. If the foreground app is a character application, the OS will restore the screen itself. If the foreground app is a graphics application, then that application will be notified to restore its own screen. I'd like to discuss how you can program the video hardware directly from your application. I would caution you that if you do this, your application instantly becomes hardware dependent and may not run on all OS2 machines. You'll have to have support in your application for each type of video adapter your application is supposed to run on. Our recommended method of doing graphics output is to use the presentation manager. And I think that you'll see that doing direct video output has a lot of disadvantages and a lot of complexities that will discourage many people from using it. OS2 provides 4 main functions to allow you to program the video hardware directly. There's a function called VIO set mode, which will put the screen into any desired graphics mode. In order to use this function, you need to know what type of graphics adapter is installed on the machine. Second thing we provide is the IOPL segment, which is a method of using in and out instructions directly from application level code. This is needed for some video cards, such as the EGA, where you need to be able to program the palette registers. And again, you see that your application is very hardware dependent when you're using these functions. Third thing we provide is a call to get the address of the video display buffer. The function call is VIO get FizzBuff, and it returns a selector or multiple selectors which map the video hardware memory. Again, in order to use this effectively, you need to know the characteristics of the video card you're working with. Some video cards have more memory than others. Finally, we provide a call VIO screen lock, which enables you to synchronize with the application being in the foreground screen group and to lock the screen and prevent screen switches for a short period while you're updating it. Threads in applications which are writing to the screen directly will be frozen while they're running in background, since we can't support direct programming of the video hardware in background mode. As I mentioned earlier, a foreground application that has the screen in graphics mode is responsible for restoring its own screen after the system has put up a pop-up message or after a screen switch from another application. The reason why we make this the application's responsibility is really twofold. The application can probably do it more efficiently than the operating system, since if the OS were to do it, we'd need to save all 128K on an EGA, whereas the application can probably restore the screen from internal data structures with far less memory than that. Secondly, some video cards are not arbitrarily restorable if you preempt them while they're being written. The way we have applications synchronized with screen switches is that they provide 2 threads, and those threads wait on system calls. One is VIO save redraw wait, and the other is VIO mode wait. These system calls will return to the calling thread when they need to redraw the screen or refresh the current video modes. So I've covered screen output. We discussed the functions that are used by most applications for character output, cursor positioning, and scrolling. And these are the bulk of the calls beginning VIO. Then we have the call for putting up pop-up screens, which is a function that could be used by certain background applications. And then we have this small set of calls used only if you're writing directly to the video hardware. Now let's take a look at mouse input. OS2 provides a set of functions that are very similar to the interrupt33 calls available in real mode with the Microsoft Mouse device driver. In the software development kit, you'll see these calls all begin MOU, and they provide functions for reading button transitions, cursor positioning, setting the cursor shape, and querying information about the mouse position. Now I'd like to discuss a mechanism by which an application can intercept screen, keyboard, and mouse functions. This is a very specialized set of routines that will not in general be used by applications. They're present in OS2 to support Microsoft Windows or any other window management software that needs to intercept console output from all applications within a screen group. What this service provides is a mechanism for you to replace any individual VIO, KBD, or MOU function on a per screen group basis. And you have to provide your own routine to replace the one that's provided with OS2. If you've programmed under DOS 3, you'll see a lot of similarities to hooking interrupts. And what we tried to do here was provide a more robust method of achieving the same type of result. On this diagram, we see four main components. On the top left-hand corner, there is an application that is writing to the screen. I'm going to use VIO as the example here, but everything I say applies to the KBD calls and the MOU calls as well. This application has two ways of writing to the screen. It can do a file system DOS write call specifying the handle to the screen device driver, or it can call VIO directly. In either case, OS2 ensures that the call ends up in the VIO dynamic link library. In the case of a VIO call, the function goes there directly. In the case of a file system write, the function goes to the operating system, which then redirects it to the VIO dynlink library. The standard VIO dynlink library provided with OS2 consists of a routing package and then a package which actually implements the screen output functions. And it's at the level of the router that you can replace functions. On the right-hand side of the screen, we see a replacement VIO dynamic link library. It can be one of these per function in each screen group. And when any VIO call arrives at the router, it will decide whether to pass the call to the standard package or to redirect it to your replacement routine. In either case, the action is expected to end up on the physical display. It's important to note that what I'm discussing here is a control flow interception method. You should not get it confused with character device monitors, which is a method of intercepting the data stream to a character device. Here we're intercepting the flow of control and redirecting it to a different library routine. Now, as I mentioned at the beginning of my presentation, most character applications are able to run on the Windows Presentation Manager desktop. There's a few restrictions you have to follow in order for this to be true. These are the most important ones. You should not use keyboard monitors. You should not do any direct hardware graphics output. And you should not attempt to replace any of the VIO, KBD, or MOU functions. I think you'll see this is a fairly small set of restrictions, and in general, most character applications, including things like the Microsoft Assembler, the compiler, these will all be able to run in a window on the Presentation Manager. If you don't follow these rules, then the Windows Presentation Manager will start your application in a separate screen group with a full screen rather than in a window. People often ask whether character applications can use just a few of the Presentation Manager services, maybe for graphics output. The answer is no. You can't use a few of the Presentation Manager services unless your application conforms fully to the Presentation Manager model. Okay, that concludes the first half of my talk. I've discussed the what a character application is, how you would start one up. The main areas of difference are the keyboard, the screen, and the mouse. We've also looked at character device monitors, which are a method of intercepting the data flow on a character device. Now I'd like to move on and talk about family applications. These are a type of application that conform to a subset of the full OS2 character application interface, and they are able to run under OS2 in protected mode on a 286 or 386, under OS2 in the compatibility box on a 286 or 386, or under MS-DOS version 2 or version 3 on an 8086, 88, 286, or 386. So you see, these are the widest possible range of installed base applications that you can achieve. And I'll be discussing the type of restrictions that you have to obey in order to achieve this. This diagram shows what a family application looks like. It's built as an exe file, just like other OS2 applications. If you look in the center of the diagram, there's a header, followed by the bulk of your application, the gray area, and then two pieces attached to the end. There's a stub loader and what we call the bindings. The bindings are a library which translate from OS2 calls into MS-DOS interrupt 21 calls. The stub loader is a loader which understands how to bring this new exe image into memory in the DOS 3 environment, and will fix up any references from your application to point at the library. Here we see a family application and which components are used when it's loaded in memory. On the left-hand side, we see that there's the application and it's making system calls directly to OS2. On the right-hand side, the same application is loaded in real mode, and what we call the API library sits between the application and the MS-DOS operating system, or the OS2 compatibility box. And this library, or the bindings, is the piece that translates the application OS2 calls into MS-DOS type system calls. Let's look at how you would build a family application. The steps you take are exactly the same as you would for building a normal protected mode character application. You have your source code, run it through the compiler or the assembler, take the object files from that, run it through the linker, and you get a protected mode executable that will run under OS2. You can then take that executable and run it through the bind program which we provide in the software development kit. This attaches the API library and the stub loader. And at the end of this process, you get the family executable. I would say that all of these things I've described you can do today with the software development kits you've received. The bind utility, the API library, and all the information is present in the SDK. Now I'd like to spend a couple of slides looking at the type of restrictions you have to follow when you're building your family application. First, obviously, is that if you intend your application to run on an 8088 or an 8086, you need to steer clear of any of the 286 specific instructions. In assembler, we have assembler controls to ensure that you don't accidentally use any of those. With the compiler, there's a command line switch to control the code generator, and you use /G0 to disable any 286 specific instructions. If you only intend your application to run in the compatibility box of OS2 or protected mode, then obviously you can use the 286 instructions. It's only if you need it to work back in the DOS 3 environment on 8088 machines do you need to watch out for this. From a functional standpoint, OS2 clearly has many more programming interfaces than MS-DOS. And you will see in the Software Development Kit Programmer's Manual, there is a core set that are defined to be the family API. This is shown in this diagram as the center rectangle. Outside of that core set, both MS-DOS and OS2 have functions which are not suitable for use in the family API model. Under MS-DOS, an example would be the FCB method of doing file I/O, or some of the calls for hooking software interrupts. These cannot work in protected mode, and so they're not supported as part of the family API. Under OS2, there are many multitasking functions, thread creation, asynchronous execution, semaphores, in general, most of the IPC mechanisms. These cannot work back in the MS-DOS environment, and so are not part of the family API core. Your family application clearly has to be able to fit in the 640K environment of DOS 3 or the compatibility box. When the same application is running in protected mode, it will have the benefit of much larger memory. Your application, as I said, must not use any of the threads or asynchronous execution features. There are some semantics of the file system, such as global versus local current directories, that you may need to be aware of. And there are a few functions, such as DOS open and DOS exec, which have many different parameter options. And you will see from the documentation that only some of these are supported in Family API. For example, on DOS exec, you can exec a child process synchronously in Family API, but the asynchronous execution option is not available. So having described this core set that works in both real mode and protected mode in the Family API, I'm now going to describe what you do if you need to use some function that is not available in both modes. We have a call DOS get machine mode, which will return to you the current machine mode. It returns either 0 or 1 for real or protected mode. This is not the same as calling DOS get version. The version number of the compatibility box is exactly the same as protected mode under OS2. So if your family application needs to have code in it that is sensitive to whether it's real mode or protected mode, you should first call DOS get machine mode. This little code sequence shows how that works. DOS get machine mode takes the address of a flag, and on return the flag will either be 0 or 1. Just backing up there a second, the type of things that you might do in your conditional code in your family application would be access the mouse, for example, which does not have a family API interface. In real mode, you'd go ahead and call interrupt 23, and in interrupt 33, excuse me. And in protected mode, you'd go and call one of the MOU functions. Now, there's a number of performance and size costs associated with using the Family API. There's really three areas you need to look at. There's the size on disk of your application, there's the size in memory when your application's running, and there's the execution speed of your application. Typically, we've seen applications grow between 10 and 30K when they're bound as Family API applications. This is due to the size of the stub loader and the bindings which are attached to your application. The exact amount of size growth depends on which OS2 interfaces you use. Some of the functions in the Family API translate very easily into MS-DOS functions. Most of the file system calls translate with very few instructions. However, some of the video functions and the keyboard functions don't have any direct analogs under MS-DOS, and so the amount of code in the bindings for those functions is much larger. So you have to try it with your application and see how much size growth you get. When a family application is running in protected mode, there's no size penalty in memory and no speed penalty because the bindings are not loaded and there's no code between the application and the operating system. When you're running the same application in real mode, there is some small overhead associated with the bindings that are translating the calls from OS2 calls into interrupt 21. We've seen that in most cases, for the code we've tried, this overhead is almost negligible. In the software development kit, the assembler and the compiler are bound programs, and you can run them yourselves and see what the differences are. Now, in real mode, your application will have a 10 to 30K memory size cost associated with the bindings. And again, just like the disk size, This depends on the set of functions your application is using. Finally, in real mode, the application will load somewhat slower than a corresponding old exe or com file of similar size would. This is because the new segmented executable image has more complicated structure and is slightly slower to load. We can't just read it in as one disk read. So that concludes the section on the Family API. I've described how it works. There's a set of bindings that translate between OS2 calls and MS-DOS calls. Described how you use it. There's a bind utility and an API library which you use as the final step of your software development. There's some restrictions associated with the functions available and the type of parameters you can pass to the functions. And there's some cost in memory and disk of using Family API. At this point, I'd like to move on and take a quick look at the tools available for debugging your application under OS2. The primary debugging tool you'll use is Microsoft CodeView. The screenshot here shows typical CodeView screen used to debug a C application. In the large area at the center of the screen, you see the code of your application. CodeView is displaying the C code and the generated assembler code intermingled. At the bottom of the screen, there's a command line area used for you to type debugger commands. On the right-hand side, there's a register display and the current flag settings of the processor. At the top, we see at the very top, the blue bar shows the menu interface that you can use for CodeView. This is optional. You can either use the menu or you can use the command line interface at the bottom of the screen. The menu interface works with the mouse. Anything you can do with the menus, you can also do on the command line interface. It's up to you which user interface you choose. Just below the menu bar at the top, there's the area which displays various expressions that are being monitored while the application is running. Those of you who've used CodeView in the C4.0 environment under MS-DOS will find that all of your features are available here in protected mode under OS2. CodeView is essentially a full-screen, window-oriented debugger. You can see your source code, you can type commands, and you can see your application output on the same screen. Your code is displayed the way you wrote it, with your data declarations, your indentation, your own formatting displayed on the screen as the program executes. CodeView supports both C and Microsoft Macro Assembler. We'll display both of them in the appropriate source code. Now you can mix C and assembler within the same program, and CodeView will automatically switch from one subroutine to the next using the correct form of source display. CodeView also supports several advanced features. We have watch points, trace points, and watch expressions. A watch point is a conditional breakpoint which breaks when an expression you specify becomes true. Trace point is a breakpoint which fires when a memory location is changed. And a watch expression is an expression you specify whose value will be continually updated in the area at the top of the screen while your program is running. All these features are available in the software development kit that you have now. The SDK contains two versions of CodeView, one for use in protected mode, one for use in real mode. Finally, I'd like to take a look at some of the features we're working on for future software development kit updates. We have three main areas where we will be enhancing CodeView. The first is the ability to debug dynamic link libraries. You will be able to trace from the source code of your application into the dynlink library and switch to the source code for the library. This will be in the first update to the software development kit. Second area we're working on is CodeView support for Presentation Manager applications. This will be available when the Presentation Manager component is shipped with the SDK. You'll There will be two ways to debug a presentation manager application. You can either run CodeView on an outboard monochrome monitor, or you can run CodeView in a separate screen group and switch between CodeView screen and the presentation manager desktop. I think generally the outboard monochrome monitor is going to be the preferable way to go. Then finally, we're adding support for multi-threaded applications to CodeView. You'll be able to display the stack, the registers, and the priority for each individual thread within your application. You'll also be able to set breakpoints that control individual threads.
For additional information on the topic we just covered, be sure to take a look at the written questions and answers that accompanied this videotape.